So now let's re-evaluate carbocation rearrangement. We can think of this rearrangement as essentially just another reaction of a nucleophile interacting with an electrophile. Uh, so we learned in the previous video that carbocations are stabilized through both inductive effect and hyperconjugation, right? But what is hyperconjugation? Well, if I look at a carbocation, and in this particular case I have a secondary carbocation, and it's attached to a vicinal carbon that has a hydrogen on it, and it has two methyl groups. So it's a secondary carbon, but that hydrogen and the methyl groups can certainly stabilize the secondary carbocation, right, and its empty p orbital by the overlap of the sigma bond between carbon and hydrogen, or one of the carbon-carbon bonds. Now, interestingly enough, what happens is when that sigma bond helps to stabilize that carbocation, it stabilizes it so well that it actually donates its pair of electrons to the empty p orbital. And the result is that we get this shift and the formation of a new p orbital, and or a new carbocation, excuse me. Now, this carbocation is more stable than the secondary carbocation. And so what has happened is that hyperconjugation effect has produced a more stable carbocation, certainly. It's just happened to produce it on a different carbon, right? So what's happened? Well, again, we can think about the diagram of that sigma carbon-hydrogen bond interacting with the empty 2p orbital, and we know that the sigma bond has two pair of electrons, and the 2p orbital is empty, so we have this mixing of a filled orbital with an empty orbital to produce two new orbitals, right? Stabilization. But the effect is that that stabilization produces a different carbocation that is more stable. And so we can think of this as what I call hyperconjugation at its extreme, right? That that carbon-hydrogen bond essentially donated so much electron density to stabilize that structure that it produces a new carbocation. Remember, we're looking at an overall structure, the stabilization of an overall structure, not just a carbon atom. And so, in effect, what's happening is a structure, a species, is going to look to stabilize to get into its lowest energy state possible. And this is why carbocation rearrangements occur, and they occur quite readily. If we can essentially produce a carbocation that is more stable on a vicinal carbon or a beta carbon, right? Now, because of this, we can see some strange things. And one of those things is that a carbocation adjacent to a ring can undergo rearrangement in the form of what we call a ring expansion or a ring contraction. So, as an example, here I have a carbocation that is connected to a cyclobutane ring. Now, this is a tertiary carbocation. We would expect that tertiary carbocation to be in some type of potential energy minimum in terms of carbocation stability, intermediate stability, right? And yet what happens, what we see is that we get a shift, an alkyl shift. So the vicinal carbon is going to have one of its carbon-carbon bonds break and migrate to that carbocation. What happens is the ring expands. So this is called a ring expansion. And if we number the carbons 1, 2, 3, 4, 5, we see that what's happening? Well, the C2C5 bond is breaking, and now we have a new bond forming between C1, carbon 1, and C5, carbon 5. So that I now have what looks like this. So here is C1, and now it's connected to C2, which is connected to C3, which is connected to C4, which is still connected to C5, but now C5 is connected to C1, and C1 still has the two methyl groups. Where's the carbocation? Well, the carbocation moved to carbon number 2, and therefore that's where the carbocation is. Now, if we step back and take a look at what's going on here, we see in the first carbocation I have a tertiary carbocation, but I also have ring strain. And that ring strain is going to force to try to minimize that strain because again, I had mentioned the the um, the species in its entirety is going to try to stabilize itself. So how can it stabilize? By increasing the size of the ring to minimize ring strain. So in the second carbocation, we see it's actually a secondary carbocation instead of a tertiary. And therefore, well, the secondary carbocation is less stable than a tertiary carbocation. Yes, but we get minimization of ring strain. And so because of that, we are going to get products in which you're adding a nucleophile to carbon number 2, and we're going to see this ring expansion occurring and seeing cyclopentane rings instead of cyclobutane rings. And this is certainly, some of the strange behavior that we can see. But if we understand, all the little details about it, that carbocations are going to stabilize themselves, be they from substituents that can donate electron density through resonance or inductive effect, or even a different type of strain like ring strain. We have to be aware of that, right? Here's another example where I have a carbocation, and notice on a vicinal carbon I have a methyl group and a chlorine. Now, always be aware that that chlorine is withdrawing electron density through an inductive effect. And also notice that I can get rearrangements here of the methyl group. And certainly I'm going to see a lot of different types of rearrangements with this particular carbocation. Why? Well, hopefully by now you can predict that that methyl group is going to migrate to that carbocation, and so certainly we can show that that is a possibility, and it's actually a pretty good possibility. Why? Because the resulting carbocation, even though it's still a secondary carbocation, so we're going from a secondary carbocation to another secondary carbocation, but this secondary carbocation, where I have the chlorine attached to that carbon, we've seen what halogens and what essentially atoms that have non-bonding pair of electrons can do to the carbocations. That's right. They can donate electron density, and we can draw a resonance structure that stabilizes that carbocation. That is definitely going to happen. But there's also another possibility that we have to take a look at, because it isn't just a methyl group that can shift. Remember, hydrides can shift, and alkyl groups can shift. So certainly a methyl group can shift, but I have another carbon on that vicinal carbon, and it's right there. And so when I see that type of shift, now what's going on? Well, now I'm actually undergoing a ring contraction. I start with a 6-membered ring, I end up with a 5-membered ring. But notice the carbocation that I form again is attached to the chlorine. And so that chlorine can donate electron density, and I can show a resonance structure where the chlorine is stabilizing it. So both of these types of rearrangements are certainly possible. And we would then predict that if a nucleophile is going to attack that carbocation, it's going to give me, substitution at at either one of the carbocations that we underwent rearrangement for, and I can predict why that's happening. So that's one of the things that you need to be able to do. If I show you a reaction and I show you the products from that reaction, and those products are kind of not what we would initially predict, you need to be able to figure out why we're getting the products that we're getting. And in almost all of those scenarios, it's going to be based on some type of rearrangement and stabilization through a substituent that is on that structure. Okay?